Okay, so good morning and welcome back to today's TIFR's ASSET Colloquium. ASSET stands for Advances in Science, Engineering and Technology, and this is a forum which mainly organizes talks relating to the detector, electronics, the data accumulation systems, software, and topics like that, which are mostly connected with all the engineering and technology issues, right? And today it's my great pleasure to host on the ASSET Colloquium one of our department colleague, Ms. Mandakini Patil. She's going to talk today on highlights of the front-end electronics work at TIFR for the CMS experiment at LHC. Of course, CMS stands for Compact Ion Solenoid. Just to say a word or two about today's speaker, Mandakini did her MSc Physics with Electronics from Mumbai University, and in fact taught for about a year in the SIES college in Mumbai. She then joined TIFR in 1990, initially working with low temperature physics group for about a year. Then she joined the experimental high energy physics group, where she has been since then. And she is a scientific officer EF in the Department of High Energy Physics. She was, of course, involved in a number of experimental projects. The most important being what she's going to talk today on is the CMS outer hadron detector, where she was deeply involved in the installation and commissioning and testing, as well as the silicon strip detector R&D work for the Belle experiment at Japan on the KK. She is deeply engaged currently in the CMS hadron calorimeter upgrade electronics and also the CMS trigger upgrade electronics, about which today she is going to make presentation about. With those few words, now it's over to Mandakini. Mandakini, you are muted. Can you please unmute?
Okay, sorry. Yeah. So good evening, everybody, and thanks, Satya, for introducing me and also for giving me this available slot for ASSET. As most of you know, I'm, as also introduced by Satya, I'm mostly working for the HCAL and CMS experiment, and I'll be talking about the highlights of my contribution on behalf of our department, with a more focus on the contribution specially made by me and my team members under me, so working under me. So I think I'll share, but maybe I'll just put off my video, because otherwise I think it will be difficult for me to continue with the same bandwidth. Let me just put off the video 1 minute. So I think people can see the screen, right?
Yes.
Yeah.
Yes, we can see.
Yeah. So on my first slide, on my second slide, as it is conventional, I'll just start with the plan of the talk. That is, I'll give the introduction and the motivation for working for CMS experiment, introducing what CMS is. Then I'll go on to HCAL electronics, the hadron calorimeter phase 1 upgrade work that we were involved in. Then I'll switch to the next topic, that is level 1 trigger upgrade. And also I'll briefly talk about, just to give a completion to my CMS related work, and also talk about the involvement in the tracker module mechanics and I mean silicon strip detector, this thing, just very briefly. And then I'll sum up with discussing the future plans for our group. So on to the next slide. Can you see the slide? I'm not.
No. In fact, your presentation is off now. Can you reshare it?
Yeah.
Yes, and okay, go to the full screen.
Yeah. Can you see the next slide? Yeah.
Yes, perfect.
Yeah. So on to the next slide, slide number 3. So I am working for the CMS experiment, which is, as you can see, is a part of the Large Hadron Collider experiment here. And the Large Hadron Collider ring can be seen. You can see the proton-proton beams that are colliding. And you can also see the 4 major experiments: Atlas, Alice, and LHCb, as well as CMS. The CMS stands for Compact Muon Solenoid. Both Atlas and CMS are multi-purpose experiment, with the international collaboration of more than 4,000 people participating in it. The major participation by TIFR from the nascent stage is in CMS experiment. So you can see the CMS experiment located here. And you can see the proton-proton colliding in the beam in the LHC ring, which is around 27 kilometers in circumference. And this is 100 meters underground in Geneva, straddling the Geneva French border, that I think many of you know about it. So coming to the compact muon solenoid detector as such, it is a mammoth detector with the epitome of cutting-edge technology, with about more than 10⁸ readout channels. And I'm extremely lucky to be associated with this international experiment for more than 20 years. So as you can see here, the dotted yellow line shows the proton-proton in the cartoon here, shows the proton-proton colliding. And surrounding the collision are the multi-layers of the sub-detector CMS. So you can see that right from the beginning, I mean, close to the interaction point is the pixel detector, which is mainly composed of solid-state pixel and strip detectors. The tracker is the next one, which is also made up of silicon strip detectors. Next is the electron calorimeter, which is mostly lead tungstate crystals. And then comes the hadron calorimeter, where we are going to focus our attention today in today's talk. So hadron calorimeter is basically a sandwiched calorimeter detector with plastic scintillator and absorber material. Then is a muon detector, which spans the major part of the ring. You can see the configuration of the ring here. It is made up of several concentric rings, and the red portion that you can see here is the ion here, and the grayish portion that you see close just after the hadron calorimeter is the return yoke of the coil. So before I really go on to tell what we are doing, I just want to give a brief sketch of the typical data acquisition system and detector readout in a high energy physics experiment. Or for any experiment also, the basic starting element is the detector or the sensor. So after that comes the front-end electronics. So depending on the signal to be measured, if it is a light emitting detector, as in our case, we need a photo readout device also to convert this light into a electrically measurable quantity. And then, so we have in addition, a photo detector, and then comes the amplifier, filter, shaper, sampler, etc., which actually forms the part of the front-end electronics. After, once you get the analog signal and you process the signal, remove the noise, etc., then you try to digitize it using good efficient analog to digital converters. Then you do the zero suppression, range compression, and other kind of digital processing, and then you try to pass it on to the computers for online and offline analysis. But in mammoth experiments and in most of the experiments which have trigger for coarse and raw file filtering, so is the case with CMS detector also. So you can see here there is a two-step trigger here, two levels trigger. The primary or the level 1 trigger that we call, that is basically going to decide which are the, it will do the coarse filtering after deciding on which are the really events of interest, and then it will pass it the pipeline buffer that you can see here, that will actually do some processing, intelligent processing, and then pass it on to the next stage for feature extraction and all that. Then we have one more high level trigger, which actually corresponds to a fine coarse filtering kind of thing, where even more unwanted information is removed. And then finally, after the second level of trigger, the real data acquisition central farms start coming into picture, and this is where the event storage happens. So basically, it is important to have this trigger, especially for a very huge experiment like CMS, where a large amount of data is being continuously acquired, and it needs to be stored only for those events which are of interest to the students and to the physicists. So coming to the next slide, now I'll come to the real first part of the experiment, that is the Hadron Calorimeter electronics upgrade that we were involved in more than, 5-6 years from now. So before I introduce the actual work, I would like to tell what a hadron calorimeter is. As the name suggests, it's a reservoir of hadrons, the heavier particles that are formed and detected in the hadron calorimeter in the CMS part of hadron calorimeter part of the CMS experiment. So you can see that you can see the geometry of this hadron calorimeter. You can see some colored regions here in the barrel part, which is actually the central barrel region of the hadron calorimeter. And you can see towards the higher eta region, the HCal end cap of the detector. So you can see that earlier, you can see some segmentation here. So basically, hadron calorimeter is, as I mentioned, it's a scintillator-based sampling calorimeter, and it is read out with earlier with hybrid photodiodes in the legacy detector, but now it is being read out with silicon photometer, and it is continuously upgraded. For during the earlier times, the segmentation was not much, and we were combining the readout of many layers of this subdetector. But now, for higher luminosity, it is important to have more segmentation, and that is being done in this current scenario. So just therefore, it becomes more important that we switch over the electronics also. So the current technology detector component designs were based on the early 2000 technologies, and now we are continuously upgrading this electronics for the HCal upgrade. So what is this upgrade really happening, and where it is happening? So you can see here. On the topmost is, I have shown the front end picture, so you can see the scintillator emitting light. It's not the PMT currently, it is the silicon photomultiplier that is reading out the light. And once you get the light, it is going into the front end or the readout box. The readout box is shown in detail on the right side, but I'll just explain what the each component is, because this is important and this is where we have done the major contribution. So you can also see in the front end card, there is a QIE 10 gem. So basically it is a charge integrator and encoder, the ADC chip, and then there is a FPGA. This is a front end FPGA, and then you can see a gigabit transceiver, and then you have VTTX or the versatile transmitter and receiver. In order to transmit the huge amount of data from the front end electronics, which is normally sitting close to the detector, and for us it is sitting 100 meters down in the pit, and whereas the backend and the other data processing units are going to lie in the control room. So it's essential to transport the data, and this is done through optical fibers. So there is a conversion from optical to electrical, and then again electrical to optical kind of reconversion, etc. And this happens in the laser diodes that are used at either ends. You can see the red line here. So basically that is an optical signal. You can see the on the back end side there is a micro heater. Basically it is a HCal trigger readout module, and you can see also the advanced mezzanine card AMC13 and all that, which forms a part of the back end electronics. So basically this back end electronics also has now changed, and the interfaces are getting upgraded. We are using advanced technologies to cater to high speed and all that. I'll come to that in more details in the subsequent slides. So on the right hand side, you can see the typical readout box. You can see that there is a optical decoder unit that is seen in the very initial stage of the readout box, which is shown here. The one readout box, which is a 20% slice of the entire CMS HCal detector, is enclosing 4 readout modules that you can see here. So in addition to the 4 readout modules, there is a clock and control module, and there is a calibration unit. So the clock and control module basically is in continuous communication with the front end electronics and the back end electronics, and whenever the calorimeter trigger or whenever the central trigger is allowing us to take the data, it will try to send the data. Whereas the calibration unit is another important unit of the detector readout box, because this is where we are going to monitor the health of the electronics by shining continuous light which is kind of emulated as the light equivalent to that emitted from the detectors by using LEDs actually. And then we'll be taking data whenever the beam is off and calibrating and checking the gain of the front end electronics, the QI cards, etc. So this is a very important component of the hadron calorimeter, and so is the readout module. The readout module basically will have the QI card, and the light signal is coming from the ODU through the detector, through the ODU. It will shine on the silicon photomultiplier, and after the conversion into electrical signal, it will be amplified by the QI card that you can see here. And then you can see that the major portion of the readout module here is shown in blue color is the silicon multiplier. It's written as bias and control card, so it is silicon PM control board we call it, and you can see the bias also. So this is again a very important component of a readout module. It is a control card which is actually giving doing a lot of housekeeping. Again, this I am going to discuss in detail because this is where is a major contribution. So basically, to cater to very high speed and high luminosity, we have upgraded the data acquisition system, also upgraded to micro TCA and subsequently to advanced telecommunication architecture. Again, about this, I'll talk in details in the subsequent slides. So to the next slide. So you can see the typical readout module. This is very important. This is a real readout module. I just showed the cartoon sketch of the in the previous slide. So you can see the 4 QI cards. So each readout module, this is a readout module which corresponds to hadron calorimeter and cap detector. So you can see the control card, silicon PM control card, which is marked as RM2x4 and CMS S/C. So this is the topmost card. You can see some black detectors, black small connectors also. These are basically the sensors, humidity and Peltier temperature sensor, etc., which are being read out from here. The sensors actually lie here. So you can see the on the left side, the optical decoder unit and the connectors, which will take the fiber optical cables from the detector and get connected to these connectors here. So you can also see that there are some adapter boards and the QI boards, etc. So this whole assembly is a very delicate and complex one. I have been participating in this assembly during the installation of our silicon PM control card, which we fabricated here. So in the next slide, so I'll just focus and tell that we have mainly two types of contribution that we did from TIFR under my supervision. And the first part was the silicon PM control card, which sits inside the readout module that I showed just now. And the second one is the calibration unit, mechanics, as well as electronics. So what exactly did we do for all this? So we have fabricated more than, around 100 multi-layer pulsar boards for the calibration units, both for hadron end cap and hadron barrel calorimeter, and this was fabricated in the Indian industry. A lot of coordination and R&D studies were done before we really got into the production mode, and we actually I have interacted very closely with the engineers in the design and fabrication aspects of with the engineers of the Indian industries also. And after identifying the correct ones, we have started with the prototype development and then with the production. These pulsar boards have the microservy FPGAs, which are used for programming and sending the control light LED light that I told to calibrate the silicon photomultipliers. So this is the first time, I must say, that I got really introduced to the microsemi, to the FPGA concept itself, the field programmable gate array concept basically. So this is the first time I really got introduced, and it was really exciting and interesting to understand what a FPGA is, how it works, and I never knew that I'll be working more involved in the later stages for inside in the using this FPGAs very intensely. We also made 400 silicon PM control cards and 400 bias voltage cards. Again, these are all multi-layer cards which were fabricated in the Indian industry. We have tested all these boards in-house using a standalone test which we have developed at TIFR using some embedded microcontrollers, Raspberry Pi in our case, in some cases. We also, in addition to the calibration unit pulsar board, we also have some pin diode boards. 300 pin diode boards were made here. The PCBs, in fact, only we got it done from the local industry, and entire wiring was done in our in-house by TIFR technical staff. So I was involved in the entire this, and some of them, I mean, even the pin diode modification, the circuit design modification for biasing, etc. I was involved in that also. And also we have tested all, I mean, we have fabricated and assembled all this in the calibration unit. We also had to make 150 each for each calibration unit, charge integrator and encoder adapter cards, which actually connect the pin diode outputs to the QIE input cards. So after quality assurance, these were shipped to CERN at regular intervals. And initial very prototype fabrication, we had some rejections and some teething problems, but we corrected them by some suggestions, feedbacks, and continuous interaction. And we were updating all this to the HCAL community on a regular basis. Coming to the real picture of the front end electronic board. So you can see on the left hand side, we have the pulsar board for the calibration unit. We have the silicon PM control board. We have the QI adapter board that you can see here, which has very small connectors from Heroes company, actually Heroes connectors. And the other end of these cables you can see are connected to the back end, to the front end of the pin diode board. These are the small pin diode boards that you can see here. On the left hand side, we also see a bias voltage board. So this is for outer hadron, and hence this is for end cap hadron calorimeter. That is why it is called as HE. So you can see here the bias voltage board is also seen on the left side, which actually along with the silicon PM control board is responsible for the, it is a mezzanine board for the silicon PM control board. So the silicon PM control board shows here the BV board sitting on it, you can see here. So all these were fabricated in the Indian industry. And in the pulsar board, you can also see some white color pluggable units. These are the DC to DC converters, which we got from CERN, and we have been we had to install this, and before we really power on the pulsar board and check all that. So this was also a very crucial step in our QC. So coming to the next part of the fabrication work. So we have also calibrated around 50 hadron end cap and 50 hadron barrel calibration units. So you can see the calibration unit mechanics shown here. So entire calibration unit mechanical machining work was done in TIFR Central Workshop. And on the right hand side, you can see the various inner components. So the front end panel of this calibration unit is a bit complicated. You can see that there is an optical box also with fibers here, connectors here. There are SMA connectors, there is a LC connector, and then on the right hand side, there is a card pack box. So you can see the pulsar card here, which is sitting here. So the pulsar card, the LEDs, and all this QI connector, adapter boards, pin diode boards, etc., sit inside this calibration unit. So the entire sharing was, assembly was done by us actually. So this is again a very time consuming work, and the entire, actually when we just started with the hadron end cap work, we started it with a very short notice, and it was really a challenge to complete this in on time. And we have really put in, all our staff members have put in a lot of work, and we all enjoyed it. Now coming to the calibration units of hadron barrel, this is slightly different. Instead of a two box structure, it is now you can see that it is a single thing. So the major components are more or less same. You have a optics box, you have LEDs, you have SMA connectors, you have laser fiber connector, and you have the pulsar board. But here a lot of from the experience of the earlier HCAL NCAP work, we suggested a lot of modifications, and that was incorporated here, and we could handle these calibration units in a more efficient manner. all this, each of this mechanical work, mechanical unit, you can see that has 13 plus 17 and then 100 boxes. So more than 1200 1300 parts, actually aluminum parts, and each of this you can see has lot of many holes and screws here. So all this the entire tapping work was done by our EHEP technicians, and in fact we needed special taps and all that. So the technical people of our group, they were continuously corresponding and coordinating with the central workshop engineers as well as our collaborators, and we could do this again in a timely fashion. Now coming to the front end electronic board, this is just for the head-on barrel part. You can see the mezzanine board here, and you can see the 12-layer board. And so here again, the mezzanine board is slightly different, and the difference between the HE and the HB board, silicon PM control board, is here this is 64 channel, whereas that was 48 channel board actually. And instead of the small bias voltage board, now it has changed into a new this HB mezzanine board. It was using basically a Cockcroft-Dalton multiplier, and that's how the bias voltage of 68 to 70 volts was achieved by multiplying the input of 9 volts actually. So this was again done by the bias voltage board, which we tested here. So coming to the real HCAL silicon PM control, I mean pulse pulsar card, actually this is not silicon PM, sorry. So you can see that this is has two independent LED channels. There is a digital to analog converter output. There is a delay chip actually, 7 delay chip, which actually is responsible for producing a controllable LED pulse, which can be programmed with this micro semi FPGA. It also has a lot of regulators and for powering the pin diode boards, and then pin diode board is then has an interface to connect to the voltage supply connector sitting on the pulsar board. So the entire testing of this pulsar board was done here. I'll show the test setup stand and all. I may not be having time to focus to completely cover the test results and all that, but I will give a glimpse of whatever we have done. So coming to the next important card, this is the HCAL silicon PM control card. So you can see that for HE it has 48 channels, and for HE it has HB it has 64 channels. So its important function is to view accurately the silicon PM bias voltage and current. It also drives the Peltier element for silicon PM. It also measures the temperature and humidity of the silicon multiplier envelope, and it also does miscellaneous housekeeping like checking the bias voltage and the input voltages and the supply voltages and all that. So it has basically the circuit has basically 6 multiplexes that you can see here, and it uses two 12-bit ADCs actually, and some registers which I have not shown here, through which we communicate using I2C bus, and we are able to set the voltage by communicating with these registers and storing the values in the registers. So the two ADCs are responsible for measuring the voltages and the bias voltage that is being supplied here. So this is the actual quality control of the quality control test setup that you can see here. So you see here that we have the real back plane is seen here. So since we don't have the readout box component here in which we can integrate and test it, we had got the back plane, which is emulator of the real system, and we have a clock and control emulator also. So using a Raspberry Pi board, we wrote a simple Python Qt interface was developed in-house, and using this Raspberry board, we were able to communicate with the clock and control module. We were able to communicate with the different modules that are sitting inside the various slots. So you can see the silicon PM control and mezzanine board sitting here, and on to that you can see the fan out test test board. So basically, on the basis of the two connectors that were lying as the output connectors of the silicon PM control board, we could connect the silicon PM, actual silicon PMs, which is installed inside the readout module. Since we didn't have the silicon photomultipliers, we used a resistive load that you can see here through this flexible flat cable that you can see. So we designed a fan out test board, and we connected the resistance board equivalent to the silicon photomultiplier, and we checked the bias voltage, which is we did the calibration of all the 48 as well as the 64 channels of each of the silicon PM bar by giving the voltages. In fact, the operating voltage of the silicon photomultiplier is something like 65 volts or something. So we in fact tested, did the calibration for some voltage less than 65 and more than 65, and we had to repeat this entire test at CERN also before we really installed it in the actual readout module. So I in fact got a switch box and analog multiplexer card there. So instead of manually probing the resistance each channel and doing the measurement with a voltmeter, we could automate this setup there, and by modifying the Python Qt interface and interfacing it with the lab Windows code, etc. So we were able to in fact reduce lot of manual effort and make this entire system automatic. So we use the Keithley. I use the Keithley switch box with analog multiplexer card, and I designed the board here. And then this setup, therefore, we could measure, take as many as 64 into for 64 channels, 200 boards, and each board we had to take 3 readings at least. So we could do this entire data taking of setting the bias voltage, reading back the actual measured voltage, and then calibrating it using this setup here in a very fast manner. So this was this saved actually a lot of physical manual work, and also subsequent errors that may come because of manual probing, etc. So you can see that this is the real plot. I mean, this is just a representative plot that I've seen. So for each channel of a silicon photon multiplier card, we apply the voltages, 3 voltages, and then measure the voltage across the lot. We find the difference between the actual measured voltage and the set voltage, and then take give it to the and try to find out the offset for each channel, and then measure the mean and standard deviation. So by doing this kind of measurement, again we compared the tests, the readings that we got along with the and try to find out the correlation between the CERN measurements and the TIFR measurement, and we found that correlation to be very strong. You can see that on the top right hand side where we have plotted the offset for 66 boards. So the measurements are plotted on the y-axis, and on the right hand, on the x-axis, we have the VL minus V0 by V0 thing. So these are the offsets. So if there was any outlier or any channel of any board which was actually not within the required tolerance, then easily this plot could show up that outlier thing, and we can therefore make out that that card has some problem, and then we could, of course, while doing the measurement itself, we could detect this, since the number of votes were on 200, but this was a another more automatic way of reflecting the same in the QC of the card. And you can see on the left hand side, we are also having a calibration curve for each channel, and the slope intercept of this is, was therefore an important quality control parameter that we were testing actually. After once we have done the fabrication testing and in the standalone setup, both in TIFR as well as in CERN, it was further required that we actually integrate or install the card in its real place, that is in the readout module. Now, the readout module, as I mentioned earlier, has 4 readout modules sitting in one readout box. And you can see here the burn-in of multiple front-end readout boxes. Some of the readout boxes which are actually taking the data are also seen to be covered with black things to avoid the light leakage, etc. So, and you can see on the right-hand side the burn-in back-end fibers and the back-end patch panel fibers, because we are actually taking data from multiple readout readout boxes, multiple readout modules, and inside the readout module, we have again multiple readout channels from a single card. So you can understand the amount of complexity that was involved. So I was responsible for the validation of our first batch of Indian silicon PM control cards, and I took part, and we had to get the right signal. Of course, we were not really connecting to the detectors in this test stand, but we were doing we took lot of data with LEDs, calibration and all that, but in an integrated fashion. So you have both the back end as well as the front end here, as in the real system. And now I'll just switch my handle to a new work, that is the current trigger upgrade work. So what is trigger basically? So trigger is nothing but a complex decision that is taken in very few microseconds. So the level 1 trigger in our CMS experiment, it receives the detector data at the full 40 megahertz collision rate of the Large Hadron Collider. The detector information is inspected, and it provides a fast decision whether to throw out the event or to keep the event. So we do the level 1 trigger basically does a very fast reconstruction of each event, and then it determines whether the event has to be read out from the detector or whether it has to be passed on to the next level. So what it really does is it reconstructs the particles within one subdetector. It does it in two different ways, and talk about it in again detail, regional way as well as global way. So what is the challenge here? The CMS level 1 trigger event rate will increase continuously because we are upgrading the instantaneous luminosity of the LHC. So the task of this trigger, again, just to repeat, is to identify the interesting events and judiciously within a very short interval of time, so that we don't lose the next event which may be interesting. We have to filter out the event and store if necessary. So you have to know that the occurrence of this interesting event is going to be completely random. So the main challenges in this high luminosity is the large data throughput from the detector at this collision rate, and then the latency for processing all this thing. Presently, it is 4 microseconds, but in the new higher luminosity thing, we are upgrading it and allowing a time of 12 microseconds to combine information from all the subsystems. So how is this mitigated actually? So we are using a dedicated all FPGA hardware system with time multiplexed trigger, and so that lays a very important constraint that the first layer of the trigger card has to be very, very powerful, and it has to be flexible and compact one, and this is positioned at the back end of the detector system. So it is mainly made up of the custom made hardware. So just to reiterate, you can see that you can see the different parts of the trigger here. The calorimeter trigger or the leftmost shows a BCT or the barrel calorimeter trigger, and the global calorimeter trigger, which combines information of data inputs from detector from more sub-detector, and that's why it is combined called as global calorimeter trigger. So here on the level 1 hardware, earlier the bandwidth was 100 kilohertz. Now it has increased to 750 kilohertz, and while the next level of the higher level trigger, the rejection ratio is same. From 100 kilohertz, it is now 1 kilohertz, and it has changed to 750 kilohertz to 7.5 kilohertz. The data throughput rate is very high, as I mentioned again, 2.5 gigabits per second. And what is again important here is to use very fast electronic and see that we don't lose any event. So we have successfully delivered an excellent quality HCAL electronics in the timely fashion. And with this experience, now we became ambitious to get involved in the trigger electronics, which is definitely a more challenging one. Again, we have got involved first time from the R&D stage itself. This has definitely a lot of scope for learning and interaction, and we plan to contribute to the various different types of mezzanine boards for the main trigger board, which is meant for the calorimeter trigger. So the important crucial aspect of this trigger hardware is the calorimeter trigger uses advanced processor board that is based on the advanced telecommunication architecture, and it is using high-end ultra scale FPGAs, and Xilinx ultra scale plus FPGAs are used. The data transfer across the cards are using optical cables. Again, high-end Samtech 5 modules are used, which can transfer data at a very high speed, that is 100 megabits per second to 28 gigabits per second. So using again high-end transceiver. We are at some stage also going to make some optical cables for the data transfer, and in fact we made a very small portion of the optical cables and delivered it. I'm not talk much about that, but in future we also plan to make some more optical cables as well. So coming to the recent work, that is the fabrication of the trigger detector hardware mezzanine boards. So you can see the left hand side, you can see the main trigger board here, which is seen here as having a VU9P as the main FPGA sitting on it. This is the ultra scale Xilinx Vertex 9 family, but ultra scale plus FPGA. Only the, I mean, you can see the thermal screen screen on that. The FPGA sits below that. So there are important mezzanine boards. One is Ethernet switch module, one is embedded Linux machine, and one is another one is IPMC. So we have done some and fabricated in the initial, now the prototype phase, some 10 IPMC board and IPMC boards, 10 Ethernet switch module boards, and 3 embedded Linux. The quality control of all these boards were performed at TIFR using again indigenously developed test stand. We have delivered these boards, and except for the embedded Linux machine board, ELM board, we have tested others here. I'll talk about this also. So, and the next thing is we are also contributing actively towards the trigger algorithms. I'll come to that. So what are these 3 mezzanine trigger boards that I'm talking about? IPMC is the intelligent perform management controller. It negotiates basically with the crate for power and connectivity. It controls and monitors the board conditions via various temperature sensors and humidity sensors. It also includes monitoring hardware like system temperature and power supply. And it basically provides low-level configuration support, the recovery control, that is booting, restarting, and shutting down the server. It also logs out the failure states of the system. So all this is done by the IPMC. And next is the embedded Linux machine. This is also a support board, configuration support board, but it does higher level configuration supporting. So it does the booting of the FPGAs which are sitting on the main board. It configures the memories, and it also configures the clocks. I mean, there are a lot of programmable synthesizers and clocks, a lot of optics transceivers sitting here. So it is basically giving the high level configuration support for that, actually booting of this. It also acts as a primary network connected endpoint on the board during the online operation. And the next one is the Ethernet switch module, which is nothing but basically an intelligent hub, you can say, intelligent modem or something. It connects the onboard endpoints such as the Linux and the IPMC to the crate switch inside in an ATCA hub slot via the backplane connection. So I'll just talk in short about these boards. So you can see that these are the 3 boards, actually 3 type of boards that we have been done. The front and back side of each board is shown in the left hand side and right hand side picture. The topmost is the Ethernet switch module, and the lower side is the IPMC, Intelligent Platform Management Controller. On the right hand side is the embedded Linux machine board, which actually uses a ARM processor, embedded Xilinx SoC that is mentioned here, ultra scale plus FPGA. So this is again a big challenge to work with the SoC embedded card on here. So this is the we got the carrier code, as you can see here. This is a standalone method of testing the Ethernet switch module. So basically, we did some loop-based tests, and then each of this board has 6 ports, and we had to test the test if it was the ports were up for a transfer of 1 gigabits per second. So that by using loop cables and all that, and connecting it to the computers and modem ports, we have been able to do that. Before that, of course, we had to actually use a ASIC programmer, and using on the flash interface we were able to actually, there is a ethernet programmable switch I see here. So we updated the hardware to the onboard switch processor via the flash interface, and then after that we have tested it. So each port of the out of the 6 boards were tested by with loopback cables for the link, and the link up status can be seen here on the left hand side. Each port was tested for data bandwidth, and there was no packet loss found, and all the ports showed activity of nearly 16 gigabits per second, 16 gigabytes per second basically. So you can see here now is the second part, that is the IPMC test setup. Here we needed to actually mount the 2 IPMC board, and basically we had a Python test suite to connect to do the connectivity test. We can't test the entire functionality of the IPMC board, but basically we wanted to verify that there is no pin shorted or floating and this we could do using the Python test suite and interactive serial console. And you can see the carrier board and the installed board. These boards are again having this DIM connectors, and the verifying. There were issues in the very beginning in the first batch, but then we could resolve that. I mean, the manufacturer had some, the fabrication company had some issue making the connector, but finally it was resolved, and we could actually fabricate successfully and test the cards in-house. Now in the last stage, now we don't have the ALM test board just now set up at TIFR. So we are in fact developing the entire test suite for this. So this we are trying to understand by understanding what the embedded Linux Mezzanine board has. So you can see that it has a ARM core processor. It has several peripherals, several Ethernet control boards, USB ports, UART controller, memory chips, and DDR and QSPI and all this. So the entire FPGA and ARM processor is can be divided into 2 parts. That is the PS part and the PL part, and there are several AXI interconnects that you can see here. So basically, in order to develop the test suite for being able to test all the peripherals which are lying on this embedded Linux machine, we are thoroughly trying to understand this board, and my colleague Kushal Bhalirao is actually doing a lot of work in this, and this is the current ongoing work. So you can see that it is a small device basically based on UltraScale Zinc FPGA, and its main purpose is to serve as the onboard control interface for the ATCA modules actually. So the test firmware that we are developing basically should have a provision for testing all the implemented external interfaces. So you can see that these are the various interfaces that I have listed on this board. We have several I2C memory devices with MAC addresses. Then we have EPROMs. We have UARTs. We have I2C interfaces on board for device configuration, USB ports. Then there is a SD card. There is gigabit net interface module. So we are actually developing a integrated test suite which will be able to program, or the firmware will be able to use the driver codes that we are going to write are going to be used for testing all the peripherals on this thing. So this is the ongoing work, and we are quite progressing well, I would say. In fact, the DDR part of the driver is already written and tested, and since we don't have the ELM board sitting on the main trigger board at TIFR, we are able to do it remotely because it is installed. Our ELM boards are installed on the main trigger board in Florida University, and we are able to access the machine there, and we are able to test it remotely by logging into that. So this is again a challenging thing, but so far we are doing very well in this also. Then coming to the next part of the work of our CMS level 1 trigger, we are contributing towards the trigger algorithms also. So basically, as I mentioned earlier, the regional calorimeter trigger and the global calorimeter trigger, these are the two cards which are actually going to do clustering of the information in a regional manner and in a global manner. Basically, the regional calorimeter trigger is going to form regional clusters by combining the information both from electron calorimeter and the hadron calorimeter. The electron calorimeter has various crystals. So all the crystal information will be combined, and then we are trying to make a matrix out of it and decide which part of the information has to be combined with the physics studies and keep it form the regional calorimeter trigger. The same thing with the fiber global calorimeter trigger. The common part of each of this trigger card is each of them is independent. I mean, there's no sharing between the various cards, and the allowance of time again we have for doing the data processing is 4 microsecond of latency budget. So the algorithms which we are developing and testing, they have to be having a latency of less than 4 microsecond. So what exactly are we contributing and how are we doing it? So as you know, when it comes to FPGA, we should be knowing about the hardware descriptor language to be able to talk to the FPGAs. So the Zinc UltraScale Plus FPGAs with very high powerful ARM processors embedded and system on chip embedded on it. It will be difficult for us to keep writing HDL codes and rewriting them. So Xilinx is providing us with a new tool, which is actually Vivado high-level synthesis, and therefore all the trigger applications are now written in high-level languages, either C or C++. So how we start with this work is first we verify the functional integrity of the design by writing test benches with a set of vectors, and then we analyze this Vivado HLS code that we have written, reducing the design cycle time and mitigating the cost of the resources. We also do the RTL co-simulation, which is provided in the Vivado tool, and of course finally we do the import implementation of this by doing the static timing analysis, and also the post synthesis and post implementation, evaluating the various parameters and outputs that we get from this. So here it is important to provide the correct constraints and optimization directives to optimize the latency and resources. So this is again an entirely new domain of work for us, and along with Bhalirao Kushal, we are able to do this well, progress well, and in fact, the one for the RCT and the global calorimeter trigger code, we have been able to concentrate on reducing the number of clock cycles it has taken to complete the set of instructions, and also we are able to actually do the resource utilization optimization by using the correct pragmas and directives. So a lot of new concepts were also learned here. What is TCI, tickle command, what is IP creation, how we import. So the Vivado HLS and this new era of working with Vivado HLS and SOC has given us a lot of insights into the new concepts. And this was again a very challenging work. So what was achieved is for one such RCT code, using proper pipeline and optimization pragma, we could reduce the 45 clock cycles from 730 light cycles. There was a error of negative stack, which was again reduced, and you can see the snapshot of the post implementation report that you can see here. And similarly, for GCT algorithm, the negative slack was removed. So this is also a good achievement, and we could, of course, we had to mitigate the this problem with a trade-off between latency and design constraint. So number of resources slightly increased, but that was fine. I mean, we can live with it. So we will continue to work on this trigger algorithm work, and hopefully we are in fact involving students and others also to get involved in this challenging work. Now, just to give a finishing touch to my CMS related work, I also worked on the CMS tracker mechanical work. So basically, CMS Tracker is also undergoing a lot of upgrade, and all the microstrip sensors are being pixel detector sensors and microstrip sensors are being upgraded, and consequently, since the microstrip sensor is having strips of the with a pitch of 50 and 100 micron, the positioning of the strip sensors inside the strip module assembly is very important. And for that, special 1.8 millimeter thick spacers have been designed. In fact, I initiated this fabrication and in our local industry using a special material, again aluminum carbon fiber, which is basically used for better insulation, and in fact, for some of the spaces we had to do parylene coating for insulation, and this aluminum carbon fiber is having it's very soft, so it is easy to use, but again it is very delicate, and actually the initial exercise of doing this spacers in our local industry in New Bombay had some issues. We had to give them proper jigs actually. So some of the design jigs were designed here locally. Our technical person Sukant has helped us a lot in this, and during this R&D phase I was involved in this fabrication of this. I was actually guiding for the fabrication of the jigs and the spacers that you can see on the right hand side. We have also done extensive characterization measurements for microstrip sensors, both for Belay as well as CMS R&D work, and using the probe station that we have. So with the help of these measurements, it was again an entirely new domain of solid state physics that I really understood. I was very eager and happy to introduce this work to the students also, because it was very exciting to see 300 micron silicon strip, which is normally enclosed inside an IC, and we only keep hearing about it. So the students I have taken students to the lab to show them this thing. So it's very interesting, and to work with microstrip sensors on the and see the PN junction and measure the breakdown voltage and depletion voltage of the microstrip sensors. So I would say that I have kind of finished with my real work, and then I'll just sum up by saying that my future plan is to do an integrated quality control test suite, which is required for the mass production of the trigger boards. Just now, as I mentioned, the three mezzanine boards, the IPMC, ASM, and ALM are being tested in kits, and I mean just in standalone way. But we definitely want to integrate, and we are actually in the process of procurement of ATCA crate controller, and the entire backend as well as the front end part will try to integrate. We will integrate, and this instead of remotely logging into another machine, we'll try to set up the entire ATCA crate here, and this is certainly a very big challenge, but it is extremely interesting. And we also are doing the streamline of all the tests and documentation of the work that we are doing for this test stand that we have developed in-house. I also propose to organize a hands-on workshop on FPGA very soon for designing some exercises for the engineers and students. And of course, I'll keep updating the material for the basic electronics for the high energy physics application, in which I am also involved in some way. I also plan to set up small experiments with a portable data acquisition system using this DRS4 boards that DRS4 chip that we have which we have got, and this will basically be again giving some exposure to the high energy physics data acquisition using FPGA. So the students will find it exciting. So I'll just summarize by saying that. We are really being lucky to use being able to get exposure to the use of ultra scale plus FPGA, which has really revolutionized the high energy physics data acquisition. We have also got involved in the firmware development, which has increased the collaboration of the students, engineers, and physicists. And together, I think we are hoping to make more complex systems reliable and flexible. We are also programming FPGA is therefore now is also possible using the high level tools which we were never earlier exposed to. So TIFR is actively looking forward to this contribution towards the development of CMS trigger hardware boards and also in the firmware development, algorithm development, having delivered the prototype successfully. Of course, students and postdocs and a lot of engineers are having good experience, and therefore this essentially leads to a good potential career both in industry and academy for them. So I'll summarize here with this message that I invite people to join our group if you find the work interesting, and I'll acknowledge the help from the department faculty and all the entire technical and scientific staff members, the project engineers, the students, the TIFR Central Workshop, and of course the CMS collaborators from abroad, with whom I'm continuously collaborating. So this is the team at work, and many thanks. I may have missed one or two, I don't know. So just excuse me for that, because I think Sukant is not included here. So basically, thanks to the entire team who has worked continuously during the last few years for this successful completion and fabrication of this testing of this hardware work for HCAL as well as CMS Trigger. Thank you.
Okay, thank you very much, Mandakini, for really very interesting talk covering a big suite of technologies you mentioned about and also introduced about the modern FPGA devices, ultra scale devices, and also the new paradigm of high level synthesis firmware development, which also makes the non-expert, if I can say that, even to develop trigger algorithms and other things inside the FPGAs. And also nice to know that a large number of very high density boards were developed, tested, and calibrated. And what is good is that this brings a lot of exposure, as you mentioned, to the state-of-the-art electronics technologies, and we definitely hope, as you mentioned in the last slide, that this technology and expertise will, also the hardware that we develop will also be useful to other experiments. And most importantly, it was nice to know that a lot of students and other engineers have been trained in these technologies in our own organization here without, having to go to these experiments which are conducted elsewhere. And it's very nice to know that we have been contributing very heavily both to the current state of equipment and also, more importantly, to the upgrades. So with that, Mandakini, I think you are muted. Can you unmute yourself, please? Yeah, okay.
I would like to clap also.
Okay, let me first take up the questions. So if there are some questions from Zoom, I mean, of course, you guys can ask directly. And meanwhile, I'll also look for questions in the YouTube. Yeah.
Can I ask?
Yeah, Upadhyaya. Yeah, please go ahead.
Yeah. Mandakini, you had written in the last slide regarding plan to set up some experiment with DRS base. Do you have a plan to make a design and develop the board using DRS chip?
No, actually, yeah, maybe in future we'll do that. Just now we have started with the DRS evaluation board that we have, but we are we are going to procure DRS chip and design a board also. But just now we have a DRS board. In fact, I forgot to mention, we have implemented the ADC and the logic part. I mean the discriminator and coincident unit plus ADC part already. By writing. I mean, our student has was involved in that. We have
No, where actually this DRS evaluation board has all the things, correct?
yeah. So yeah, basically we have tried to fit it to our cosmic muon test stand and incorporate this entire thing. And we have tested the ADC and taken some spectrum from the cosmic muon data actually using plastic scintillators. Now we are incorporating, getting a TDC developed on that. So that also will get added soon. And we are getting a DRS chip, or DRS 4 chip, and designing our own board also very soon.
Okay, Suresh, that's okay.
Yeah, fine.
Can we move? Yeah. Unni, do you have any question?
I will come back.
Okay. Okay. So other guys can ask questions. By that time, let me go to YouTube. There are a couple of questions from the same participant by name Abhinav Chaudhary. The first question is, what are the advantages of you write SI-MPS, but I'm sure he's talking about SI-PMs over HPDs as photosensors. What are the advantages of SI-PMs over HPDs as photosensors?
Yeah, actually, why we switched over from hybrid photodiodes to silicon photomultiplier was we found that during the data taking, this hybrid photodiodes started showing discharges at some magnetic field, and that silicon photomultipliers are not susceptible to magnetic field. Of course, they also have a higher quantum efficiency and higher gain also. Only thing is they are sensitive to temperature and humidity, silicon photomultipliers. So we have to actually do the calibration for correct temperature and humidity, and that is the extra additional negative part of silicon photomultiplier. But gain and quantum efficiency of silicon photomultiplier is definitely higher, and that's why we use.
Okay. There is another question, of course, not directly connected with your talk, but probably you can answer that. Is TIFR also contributing in the development of gem detector?
Yeah, I think our other collaborating universities are contributing towards the gem detectors. I think Delhi University and BRC was involved in that.
Okay. Let us come back to Zoom, and there's this question from Ulas. It says, how fault tolerant are these designs? Kindly, okay, yeah, sorry, you're asking me to ask this question. So the question is, how fault tolerant are these designs?
Okay, so these designs are supposed to be installed and be working for next 20 years. So the burn-in test stand that we have done the test, I mean, as far as concerned, wherever we have tested, we don't think the fault tolerance is not good. It is definitely very good. So at least they are supposed to work for next 10-15 years.
Yeah, I guess the question is more, I guess it is a little more technical in the sense, do you have the design that incorporated the fault tolerant features? One could also think of like, I mean, since they have to work sometimes, as you said, for long periods, and though these electronics is a little bit far away from radiation zones, so are there, let us say, the designs take care of
Yes,
radiation
yeah,
tolerance and so on.
yeah, definitely take care of the radiation tolerance. Actually, the microsemi FPGA sitting in the pulsar board, in fact, is a radiation hard FPGA actually. So it uses a different technology in its fabrication itself compared to the non-rad hard FPGAs. And also, in fact, the PCBs that we are using, in fact, some of them we are using halogen-free materials and all that. And in fact, the ELM boards are again being fabricated using some different material with a low dielectric constant. Definitely, this design constraints that we have added is mainly for being able to tolerate it for a large period of time.
Are there any more questions? I think
Satya?
Onni said that. Yes, Onni.
Yeah, I don't have a question. I was actually I'm slightly dazed at the amount of work you had to put in within this 4 microsecond latency period, and so it's just an appreciation of the amount of details Mandakini went through. Of course, many of these things are very unfamiliar to me, but I have a feel for what the amount of work and the care needed to choose the right events at the detector. So I just wanted to say that the fact that Mandakini is also involved in the work with certain passion, not as just routine work, as something which is new, which is which she takes with enthusiasm. I just want to say that I really appreciate that spirit.
Thank you, sir.
That's nice, Onni. Yes, of course, this work, I mean, in general, the work that goes on, not only somebody asked this question, not only looking at what are the specs that we need today, what is the computing that is needed today, and so on, but often one actually extrapolates and looks at, because the development time are usually almost a decade or more. So one looks at the specs, what is needed much ahead of time. And these are all state of the art, both in terms of the components that are used and the technologies that are deployed. So it's really nice. Okay. Any more questions? Mandakini, I just want to ask about this part about the APX boards that you mentioned. And
yes.
So what's new? What is latest on this?
Yeah, actually, the advanced processor board, which is basically a main trigger board, and you must be knowing that it is kind of evolution of the calorimeter CTP7 board basically, and now it is called as the APX main trigger board. For calorimeter, it is called as APX board. For other detectors, I think it is called given other names like Serenity, etc. So basically, that VU9P, that Vertex Ultrascale 9, Vertex Ultrascale 9 FPGA, that is going to in fact get replaced. Earlier, it started with a demonstrator board, and it had some logic unit table circuits also. Now it's all integrated into the main design, and in fact the algorithms will take care of the lookup table revamping, table part also. So that is eliminated. So it is slowly evolving, and more complexity is going into the algorithm itself that are being developed. And the VU9P is going to be replaced by 13P, where the footprint is going to be the same, but the number of input links are going to increase. Just now we have 76 input links, and there is a provision with some contingency. It has to be increased. So see how many number of cards are going to are going to cater to one detector output channel. That is also very crucial. So that is why they are increasing the number of links, and that's why they are going to change that APX board FPGA itself. So the old algorithms are still going to be compatible with this 13P thing, but that is a new thing, and Definitely, again, retesting the whole algorithm on this new board will again be a challenge, and along with the online, control chips and all that embedded machine chips lying on them. So the entire integration will be done again, and the APX board itself is getting switched to a new version.
Another small question, if I can ask, the competition between, you did mention about, the communication technologies, the micro TCA and ATCA and so on, which are really like a backplane kind of technologies with a very limited, I would say, form factors, versus nowadays the FPGAs, which anyway come with hundreds of links, as you mentioned, with the global, very high speed links. You did mention something like 20 or 30 gigabits
Yes,
per
28
second.
Gbps, yeah.
28 Gbps. So how do the instrumentation now gets a trade-off between having a little bit, almost a legacy kind of backplane system, versus where you can take the data off from the boards with 100, let us say 28 Gbps. So it's how is the design in CMS goes? Do they go still with the backend things? Now gone are those days of your CAMAC and
Yes,
VME and
yes,
so
yes,
on.
yes.
And how
Actually,
do?
yeah, I should have kept the slide on that. Yeah, basically, the backplane matrix, which is definitely, of the ATCA is very, very complex. So you have different topologies in the ATCA architecture itself. So they are trying to adapt to the different backend in ATCA itself, backend topologies, and adhere to the one which is compatible with the links and other things that, and the signals that are coming from the backend part actually. I don't have a picture of that, but maybe I can show you sometime. That is one thing. And also the transceivers are also very high-end transceivers are being used to cater, and the optics are being used to cater.
Okay, let me just look at once on the YouTube. No more. So anybody on the Zoom want to ask or make a comment? If not, we must thank Mandakini for this very nice talk. Of course, Unni summarized well, but let us congratulate Mandakini and his group for getting involved with such a nice state-of-the-art work on the electronics for the CMS detector. And I sincerely hope, as I mentioned before, that these expertise will also become useful in terms of applying to the other experiments, and more importantly, training our students and young engineers. With that, on behalf of all of you, thank you very much, Mandakini, for your nice talk.
Thank you, Satya and others.
Yeah.